Yes, good morning, everyone. I'm really happy to present today the paper that I wrote with Dr. Patrick Dallasega from the Free University in Bolzano and Professor Dr. Daniel Hall from the ETH in Zurich. The title is Data-Driven Continuous Improvement Process Framework for Railway Construction Projects. I would like to start with a little introduction, the status quo in construction industry. I think all of us know the fragmentation of construction leads to really this interface integration, which is missing. So information that is made in the different phases is missing in later phases, or not all information goes through all the value chain. So the question is, how can we support previous phases from project delivery phases, so from the production? How can production data enable previous phases to avoid problems that leads to deviations? I would like to explain the deviations in a short video, the traffic jam without bottlenecks. So there is this experiment where I think 20 cars are supposed to drive in a circle in a certain speed. So there shouldn't be any deviation or any jam happening, because there is no bottleneck, nothing happens. But what we can see here, some cars are getting slower and traffic jams are missing or are happening. So here in this corner now, and we can see the cars almost standing. There will be one point where they're standing. So what is the problem? I think it's really hard to identify while watching or also afterwards, I think. So who was the bottleneck? And I think I'm coming from a railway construction company where it's really heavy machine driven, and there is this tech planning where the cars or the machines have to follow a certain tech. And this is what sometimes also happen on construction site, that machines are standing because the successor machine was slowing down on speed. So how can we identify these bottlenecks? This is a usual schedule that we're seeing on construction site and railway projects. This is a wait time diagram. It's really hard to read, I think, and it's also really hard to see how or if we are as planned in the construction. So when I look at it, I think it's, from the feedback from the site managers, it's more like a belly feeling that they're having. So how can we use data in the future to collect bottlenecks or variations in the project? So this is a little approach that we're having in the company, and we have the value chain around. And what we want to do is building a platform that collects data, that makes the data accessible for all the other phases, and also to learn for future projects. So putting the data in the center. What we propose as a framework, we want to collect, or we want to plan the process, the construction process, based on a process database. The platform that we're proposing, or the framework for the platform that we're proposing, is supposed to be in the middle. And then we want to collect production data. Also later on we'll come to that with the help of machine monitoring, exactly. And the data platform is supposed to gather the data and overlay them and find bottlenecks that we had on the projects. We have 3 different analysis methods which I will explain in the next slides. It's first of all the retrospective analysis. So we're looking at a project. We're looking at the data after the process was conducted. Then we have the live analysis, so really live collecting and seeing if there is any gap between the planned and the predictive analysis, which we will be then later on supported by machine learning, and but therefore we need to collect the first data. So I want to explain it on a little demonstration case from data that I conducted from projects. So we have really, it's just an extract. We have 2 machines. The first one is the ballast track machine. The second one is a track crane. They're supposed to start at 6 o'clock in the morning and should be finished by 12:30 p.m. So this is the wait time diagram planned, the dotted line, red for M1, blue for M2. So, and what's happening usually, the end outcome is delayed, but we're not able to identify where the problem occurred, or which machine or which process was the bottleneck or led to the delay. So, as I explained, we have the three scenarios. The scenario one is the retrospective analysis, then the scenario two, the live analysis, and the predictive analysis. And I want to show you, based on the demonstration case that I just introduced, what the functionalities of these different scenarios or analysis methods are. We start with the retrospective analysis. So what we see here, the line, not the dotted line, but the full line is the collected as-is data, the red one of machine 1 and the blue one of machine 2. So what we can see here is, what we can see here is that machine 1 is the bottleneck. So because machine 2 had to stop, because M1 wasn't performing as it's supposed to be. And what we can see here now, we can focus on the machine 1 and analyze the data of this, what happened there. So what we see here, we have between 6 o'clock and 8 o'clock, we have, we called it a green zone, production as planned. Then between 8 o'clock and 10 o'clock, there was a loss of productivity. So the machine didn't perform as it was planned. And we can also see in which area it was. So we can really narrow down the problem and have a better root cause analysis. So we can either go in that way, maybe logistics wasn't ready, or between 8 and 10, I don't know, maybe it rained or whatever. So we can really narrow down the problem. And then here at the end, the orange zone is productivity rate as planned, but delayed due to the red zone. So we have a loss of time of 1 hour in the location 200 to 300 meter, and the time between 8 and 10. So we narrow down the problem. And now we will come back later to the problem identification, and this will be the last part of the presentation. I want to go on with the scenario 2. The live analysis. So what we see here is the same. We have the machine 1 had a loss of productivity between 200 meters and 300 meters, or the data is not correct, sorry. But at the time where machine 1 is slowing down in speed, the information goes live to the machine 2, which is then be able to also slow down in order to avoid a clash in production. So what we can see here, they are constantly talking to each other, and they know that it's, or machine 2 works on the data of machine 1 and really knows how to speed up. Also at the time when there is 10 o'clock, the machine knows how to speed up in order to fulfill the schedule or adhere to the schedule, and also for machine 2. So we always know how fast the machine has to drive in order to adhere to the schedule. So here we can see exactly a decrease of speed based on data of M1, what I just said, and data-based adjustment of production speed accelerated in order to reach the planned outcome. So this is the live connection between the two machines. Then we have the predictive analysis. There is a lot of data needed for that. So this is really the last one that we want to implement as well, or implement in the platform as well. Yeah. So what we see here, production is as planned. The data of the previous problem that occurred was, the planning department was seeing the problems, or the site manager was seeing the problem before, based on machine learning supported data analysis, and the problem didn't occur on site. So this is really the vision that we're facing with the platform, and but therefore, we need to collect a lot of data. So the problem identification. Once a problem is identified, so the platform will show will identify the problem and tell where a certain gap between the as-is and the planned happened, and then this problem has to be identified or classified. So what we, the system of David Mann, the 5 whys. So we said once a problem is identified, there will be a platform or like an app where the site manager or the machine driver gets led through. So he can define, it was a machine problem. Okay, why it was a machine problem, and then we can go through the 5 whys, and in the end have different detailed problems or problem identifications or classifications. So I think it's also for the company. It's really important. Oh, by the way, I'm working at a Robotics array group. Sorry, I didn't mention that in the introduction. It's a good part to see if it's where the problems that lead to deviations come from. So either are there design problems, machine problems? Do we have problems with the logistics? Do we have problems with the workforce? Or are most of the problems based on unpredictable events? And as deeper as we go in this tree diagram, we get more detailed information also for maintenance of the machines and so on. So what we want to do with this information, we want to have as per the PDCA cycle improvement action plan. So we want to solve the problems for the future, continuous improvement, or improve the problems for the future. We also want to get that on a dashboard. So where do the problems come from, as I just mentioned, and all the information and all the improvements should go back to the process database as well. So we want to continuously improve our processes. And as a little outlook, this is the framework for my upcoming PhD thesis. So we will also the supervisor is Patrick Dallasega and co-supervisor Daniel Hall. So what we will work on is really further defining and this framework and getting it live into the company. Okay.